Okay, so today let's take a look at powers of I. That's our next topic. So let's look for a pattern here. Well, we know that anything to the first power, like what's 2 to the first? What's x to the first? Okay, anything to the first power is just itself, right? So I to the 1 is just I. Last time we talked about imaginary numbers, we said that the definition of I is equal to the square root of -1, right? So I squared is the square root of -1 squared. Now, when you square a square root, you cancel the radical. So what is I squared equal to? -1. Good. All right, so now a quick review of just an old concept here. What is x squared times x cubed? X to the 5th, good, right? Because when we multiply like bases, we add exponents, right? Just in general, a to the m, that's bad m, a to the m times a to the n equals a to the m plus n, right? Okay, so how could we use that fact to calculate the value of I cubed? Okay, right? And we're getting that from the fact that I could write I cubed as I squared times I. Does that make sense? Make sense, James? And I squared is just -1. So -1 times I is just -I, right? So how could I do, so James, how could I do I to the 4th then? Okay, you could. You could do I cubed times I to the 1. That would work. What's another possibility? Okay, we could also do I squared times I squared, which would just give you -1 times -1. That might be a little bit easier, right? So I don't have any i's involved. So what's that answer equal to? 1? Okay. So there's another way we could do this too. Both of those are fine. But remind me, what's x squared quantity cubed equal to? X to the 6th, right? Because when we take a power to a power, we multiply the exponents, right? Okay. So that's pretty handy then. We end up with I squared. In this case, we could do I to the 4th is I squared squared, which is just -1 squared, which is 1, right? Everybody see that? Okay. In fact, we start to see that there's a pattern here. We start to see there's a pattern. Couldn't I just do I to the 5th? I could write that as I to the 4th, which is 1. That's a pretty convenient one to use. I could write I to the 5th as I to the 4th times what? Times I to the 1st, yeah. Well, if I to the 4th is 1, then I to the 5th is just 1 times I to the 1st. So I'm going to get the same answer, right? Everybody see that? I just get I. Okay. And I to the 6th, I could write as I to the 4th times, yeah, right? And again, I to the 4th is just 1. So I to the 6th is just equal to 1 times I squared. Look at that. So I get the answer of -1. And I to the 7th is I to the 4th times I cubed. So I'm going to get the same thing I got for I cubed. And I to the 8th, I could write as I to the 4th squared, right, if I want to. And that's just 1. So look at the pattern I get. Every power, I have to go through, I count through 4 consecutive powers of I, and then it reverses to the, it cycles up to the top of the cycle again. James, what's I to the 9th going to be without even thinking about it? I, right? Because that's going to be at the top of our cycle, okay? So this packet writes, it chooses to use the first 4 powers of I to calculate any power of I. But there's an easier way to do it. Really, all you need to know, honestly, is that I squared equals -1, and that's it. We really just need those two powers right there. I'm going to show you a way to do this that's even a little bit better. So let's do an even power of I. Like we'll look at example 14 first. What's it mean to be even? Divisible by 2, right? So you know with an even power of I could always write that as a power of I squared. So I to the 62 is I squared to what power? 31, good. Okay, I squared is just -1, right? So that's saying -1 to the 31. What's that? Say it again. Okay, it's going to be -1. Now let's think about why that is. How come? Can you tell me why that's -1? That'll make it an odd. That'll make it negative, won't it? Yeah. In fact, what's -1 to the 2 trillion? 1, because it's even, right? What's -1 to the 1,935,101? -1, because it's odd, right? Okay, good, good. All right, so we can do any even power of I that way, right? I can always just break it up into a power of I squared. And what you're going to find is an even power of I is always either going to be -1 or 1, isn't it? Every time, okay? So I had people go to the board last time, but you guys could probably just do this on scratch paper and just give me, then you can just answer, right? We only have 2 people working on this. So let's try just a couple quick practice ones. What about, okay, quickly calculate for me I to the 100. One, good. Yes, that's good. You just do it in your head. That's good. Because it's I squared to the 50, and I squared is -1. -1 to an even is 1. Good job. What's I to the 50? -1. Good, right? Because it's I squared to an odd power. So -1 to an odd power is -1. Okay, good, good. All right, what about an odd power of I? Well, an odd power of I, we just alternate between odd and even numbers. So what we could always do with an odd power of I, like I to the 15th, is we could just write it as an even power of I times 1 extra I left over. So I to the 14th times I. So think what's going to happen there. An even power of I is always going to be 1 or -1. And so that's just going to give us the coefficient of this extra I. Look at what happened in our table up here. We looked at the first 8 powers of I. The odd powers were always either I or -I, right? So we're just trying to determine what's it going to be. Well, I to the 14th is I squared to what power? 7th. So what are we going to get from this then? -I, aren't we? Yeah. We're getting -1 to an odd power, which is -1 times I. So I just get -I. Good job. Let's try one of those. How about? Or 2. Okay, so how about I to the 99? What do you think? It'd be -1 to the 49, right? Times I, exactly. So we're going to get I squared to the 49 times I, right? Everybody agree? Because I get I to the 98 times I. So what's that going to be? -I. Yeah. We got an odd power of -1. Good job. So we get negative, whoops. So we get negative, oh, darn it. Colors aren't sticking. There we go. Okay. There is a little trick on this. I could ask myself, okay, what is 99 divided by 2? Isn't that 99 divided by 2 is 49 and 1/2, isn't it? Well, look what we get. Where's our 49 come from? There's the power of -1, and there's our extra I to the 1. Okay, see how that works? So real quick, try one more of those. What is I to the 76? Oops, not 76. Let's do 77. So what's that going to give us? Okay. So what's that going to be? -1 to an even power. So I'm just getting out of this just I, aren't I? Yeah. Okay. So this is equal to I squared to the 38 times I, which is equal to positive I, isn't it? Okay. I think you guys are pretty good on that. That was quick. Okay, so now let's just practice taking some products involving i's. So what about number 16? Okay, so look what happens here. I have to multiply -4i times 2i times -9i, right? When I multiply 3 factors together, I always have to just multiply in pairs. Like if you remember we did this example earlier, if you multiply 2 times 3 times 4, you get, what do you get? You get 24, don't you? Right? Because 2 times 3 is 6, 6 times 4 is 24. You have to multiply in pairs. Well, the same thing is true here. We're just going to multiply, it doesn't have to be the first two, but we have to multiply 2 of those factors together to get an answer, and then whatever that is, we'll multiply that by the third, right? So what if I multiply these two together first? When you're multiplying imaginary numbers, you just treat the I like a variable, just like an X. So what is -4i times 2i? -8i squared, right? So I get -8 times I squared. Okay, but here's where we have to stop treating it like a variable because I squared is different than X squared, right? What is I squared equal to? -1. So when we're multiplying imaginary numbers and we get an I squared, we're going to immediately convert that to a -1. So what's that going to do, James, to the sign of that 8? Yeah, it's going to make it a +8. We'll trade the I squared for that -1, which makes that whole product +8, right? And so then we end up with +8 times -9i. And now we just treat that I like an X again, right? So what's 8 times -9i? Yeah, there you go. -72i. Okay, give me thumbs. Is that good? Okay. All right, what about number 18? Okay, so we've got I times the square root of 3, that quantity squared, times the quantity -8i squared. Okay, I want to derive with you real quick. Let's derive another little property of exponents. If I had something like a times b squared, isn't that the same as ab times ab? Does it matter the order in which I multiply those 4 things together? Doesn't, does it? Remember, multiplication is associative and commutative. I can order the factors any way I want to, and I can group them any way I want to, right? So I could reorder them like this: A times B times B, and let's group them like that. So what's my answer? Yeah, A squared times b squared. And wouldn't you agree that I could have done that same thing if I had the quantity a times b to the fourth? Couldn't I have done the same thing? Multiplied them all out, shifted all the a's to the front and the b's to the end, and then grouped all the a's together and all the b's together? What would I get if I did that? Ah, okay. That looks like a general rule, doesn't it? I could pick any exponent. In fact, I could say something like a times b to the n, and I'm just going to get a to the n. That's equal to a to the n times b to the n, right? Okay, well, yeah, that works. Anytime I've got a product, now it doesn't work for sums or differences. If I'm adding a plus b, it's much more complicated than that, right? Or subtracting. But if I'm multiplying the product of a times b to some power, then I can distribute, right? And so look what I can do here. I could take this 2 and I could distribute it to both of those two factors, the I and the square root of 3. And the same thing I could do over here. I could distribute it to the negative 8 and to the I. And would you agree I just get something like that? That'll look good? Okay, well, what's the square root of 3 squared? 3. I squared? Negative 8 squared? 64, good. And then another I squared is another negative 1. So look, now I just have a bunch of numbers to multiply together. Negative 1 times negative 1 is 1, times 3 times 64 is just 192. Okay? Now, number 20, I want to show you something on number 20 that's kind of important here. Number 20, I can't treat those numbers inside the radical the same way I did when I was dealing with real numbers, and I said the square root of a times the square root of b equals the square root of a times b, right? Because if I multiply all those together, I'm going to get the square root of negative 144, right? Which is just 12i. Agreed? If I were just to do this, if I were to try to do something like just multiply all that stuff together, all three of those numbers, I would get negative 144, right? The square root of negative 144 would give me square root of 144 is 12, and then I get an I, right? Does that make sense? Okay. But now let's treat these separately, and let's see what happens. The square root of negative 24 is the square root of positive 24 times I, right? Everybody agree? Okay, so I could turn this one into the square root of positive 24 times I times the square root of negative 3 is the square root of positive 3 times I, right? Times the square root of negative 2 is the square root of positive 2 times I. Okay, well, if I multiply, let's rearrange those things, right? So I'm going to get the square root of 24 times the square root of 3 times the square root of 2 times I times I times I is I cubed. Anybody agree? Okay. Well, these are regular square roots of real numbers. So I can use the property that the square root of A times the square root of B times the square root of C is just the square root of A times B times C, if A, B, and C are real numbers, right? So this is all just going to give me the square root of 24 times 3 is 72, times 2 is 144, right? And that's just 12, isn't it, right? So that's just giving me 12. Now what's I cubed? Negative I. It's I squared times I, isn't it? So that's all giving me negative I. And so if I multiply 12 times negative I, I'm actually getting the result negative 12I. You see that? So that's my actual answer. This didn't work, right? This was not okay to do. The square root of a negative times the square root of a negative times the square root of a negative is not just the square root of a negative. We actually have to take into account that each of those is giving me an I, okay? So I can't, in other words, I can't just do that. I can't just say for imaginary numbers, this is not true, okay? This kind of a relationship right here, whoops. This is only true for real numbers. Not imaginary numbers. Okay? So when we're doing a product of negative square roots, we have to turn each of those negative square roots into an I first before we can do the product. Okay? Show me thumbs. Are we good on that? Okay, good, good. All right, so the new stuff for today then, the other new piece for today has to do with the definition of a complex number. So it turns out that pure imaginary numbers and pure real numbers are not the only possibilities. Those are actually kind of, well, it's hard to say rare because there's an infinite number of both of them. But comparatively, those are actually kind of special rare numbers that most numbers in the universe, if you looked at all the set of all numbers, there are far more numbers that look like this, that look like 5 plus 2i. Okay, they've got both a real number plus a pure imaginary number in the same number. These are called complex numbers. And it turns out that every number is a complex number. Some complex numbers are real, and some complex numbers are pure imaginary numbers, but the majority of complex numbers are neither. Okay? The standard form of a complex number is this: a plus b times I, where a is what we call the real part and b is what we call the imaginary part. Okay? So let's take a couple of quick examples here. Like, what about the number 3 plus 7i? What's the real part? 3. Okay, James, what's the imaginary part of that number? 7. Good. Piece of cake, right? No big deal. Okay, what about this number? What about the number 2i? What's the real part there? Yeah, it's 0. It's 0. Because if we write this in standard form as a plus bi, well, I'd have to put a 0 there, wouldn't I? Because nothing's showing up, right? Okay, so that tells us something. And what's the imaginary part, by the way? 2, okay? So that tells us that a pure imaginary number is simply a complex number with a 0 real part, okay? Now, along those lines, let's take the number, what about the number negative 9? For the number negative 9, what's the real part? Negative 9. What's the imaginary part? Well, it's just 0. Just 0. It's just the number being multiplied by I. Okay, good. So a real number is actually just a complex number with a 0 imaginary part. Okay? And if we think of it that way, it's easy to see this relationship. The set of all complex numbers that can be written in the form a plus bi, that's every possible number. Well, all of those real numbers that we dealt with at the start of the year, those all are just contained in a subset of the set of complex numbers. It's the subset of complex numbers where b is equal to 0, where the imaginary part is 0. Okay? The set of all the pure imaginary numbers, that's also a subset of the set of complex numbers, where the real part is equal to 0. And then outside of both of those sets, the rest of the elements of the set of complex numbers have both an A and a B that are both non-zero. Okay? All right, so then let's just try this. For a couple examples here, I want you to tell me, identify which sets this number belongs to out of these four. So -4, is it pure imaginary? Thumbs up, thumbs down. Thumbs down, for sure, right? It's not imaginary at all, is it? There's no I. So it's not that. Is it a non-real complex number? For -4, yeah. For -4, is it a non-real complex number? Thumbs down, right, okay. Because it is real, so it can't be non-real, right? Is it a complex number? It is. Every number is complex. Is it a real number? Yeah. Good. Okay, what about the number 5 plus 6i? Is it real? Not, is it? Thumbs down. How do you know? What's an easy way to tell? It's got an I in it. Yeah, so it's not real. Is it a non-real complex number? It is. You're right. It's non-real and it's complex. Is it a pure imaginary number? No. How do you know? It's got a real part. Yeah. Is it a complex number? Yeah, every number is a complex number. Okay, how about -4i? Is it pure imaginary? It is. Is it complex? Of course. Is it non-real complex? Yes. Is it real? No. Okay, and then last one, the square root of -4. Well, this is one we need to simplify first, right? What is this equal to if we simplify it? If we write this with i's, what's that look like? Okay, good. Square root of 4 is 2, and the square root of -1 is I. So we get 2i. And so non-real complex? Yes. Pure imaginary? Yes. Complex? Yes. Real? No. You got it. You guys can work for the rest of the period. That'll get you going.